Okay, at number 5, we've got a chemical reaction. We've got y equals f of t is the amount of the substance measured in grams. Oh, this sounds like an initial condition. At t equals 0, 10 grams of the substance presence. So that's an initial condition. You always want to circle that and make a note of it. And then they say that y equals f of t satisfies the differential equation given here. dy dt is equal to negative 0.02 y squared. Now, I don't know if this struck you guys as weird, but it is. The derivative they gave us was dy dt. Most of the derivatives you've seen this year are dy dx equals, and then there happens usually is a whole bunch of junk, but this derivative is usually in terms of x, which is the variable in the denominator. But in this case, the derivative is given to you in terms of y, which is the variable of the numerator. That throws a little bit of a monkey wrench in what we normally try to do here. But anyway, let's dive to it. So we're supposed to use a line tangent to the graph of y equals f of t at t equals 0, and then to approximate the amount of the substance remaining at t equals 2. So we need a tangent line, guys. The first thing we need is a point of tangency, and at t equals 0, my initial condition right here told me there were 10 grams of the substance left. So, might not be a terrible idea. At a time value of 2, we had y, meaning there were 10 grams of the substance left. The next thing we need is the slope of the tangent, which comes from the derivative. So the slope of our tangent then is going to be dy dt, the derivative, evaluated at the ordered pair 0, 10. All right, so I'm using this expression right here, negative 0.02 times your y coordinate here, which is 10 squared. Okay, now without a calculator, it might look a little scary, but I think we can handle this. 10 squared is 100. That means we're going to move this decimal 2 to the right, and we're just going to get a negative 2 now for the slope of that tangent. So we've got our point of tangency, slope of our tangent, and that would mean then that the equation of the tangent line would be given by y minus 10 is equal to negative 2 times x minus 0. So we're going to get y is equal to a negative 2x. That, of course, would be a 0, but add that 10 to the other side, negative 2x plus 10. That's the equation of our tangent line there. And now they want us to use that to approximate the amount of the substance remaining at t equals 2. So y at 2 then would be approximately equal to negative 2 times 2, which is going to be a negative 4 plus 10, and we're going to end up with 6. So that is how much of the substance we have left, according to this model here, after 2 seconds. So that was a 2-point problem here, guys. You got 1 point for coming up with the slope of your tangent of negative 2, and another point now for coming up with this approximation of 6. B was a weird question, and you guys didn't do great with it. Let's talk about why. So using the given differential equation, and I should write that down again, guys, the derivative of, the derivative of y with respect to t was negative 0.02, and then we had a y squared there. So we've got the derivative given by that. Determine whether this graph of f, which is given to us here, could resemble the following graph. Okay, so can y equals f of t be this graph right over here? And let's talk about why. The answer to this one is no. What we notice here, guys, pretty quickly is that no matter what value you put in for y right here, y squared is never going to be negative. It's always positive or 0. In most cases, it'll be positive, and a negative coefficient times a positive number is going to get you a negative quantity. So this derivative is always going to be less than or equal to 0, but basically what that means is that the differential, the equation that they gave us, is never going to be positive. And if a derivative is never positive, that means that our function f never increases. Now the question is this graph right up here a possible graph for y equals f of t? The answer to that is no, because this function right here, guys, is increasing. And in order for that to happen, the derivative would have to be positive at some particular value here of t or of y. So the answer right here is no. So we should write all this out here. No, graph cannot resemble. Okay, we'll use their word right here. The solution right here. Different graphs could not resemble the following graph. Cannot resemble y equals f of t. And let's write that out here. Because, what do we have here? dy dt is less than or equal to 0. And thus, we'll write that out, f never increases. And I think we should say, but this graph does increase I'd say on part of its domain. Okay, and I'd go with that right there. This whole thing was only worth 1 point, so they were not going to split hairs and nitpick too much there about the ordering right there, but and how we have. But yeah, that's how B works right there. Basically, the derivative is always negative, but this thing increases, and that's an incompatibility right there. Okay. Here we go. Find an expression for y equals f of t by solving the differential equation with this initial condition right here. So, diffie q, guys, dy dt is equal to negative 0.02y squared. Step 1, separate your variables. All I'm going to do here, guys, is move the y squared to the left, but not the 0.02t. So I'm going to divide both sides by y squared, and I'm going to multiply both sides by a dt, and let's see. That's going to cancel with that. dt's are going to cancel on the left, and we end up with a 1 over y squared dy is equal to a negative 0.02 and then a dt at the end of all that. So there's our separation of variables, and we'll go ahead now and anti-differentiate both sides. Now this left side we should probably think of as y to the negative second. So its antiderivative becomes negative y to the negative first power. The right side is a constant, so it just has a linear antiderivative, negative 0.02t and a plus c. This is where I always like to hit pause, and we're going to use the initial condition to solve for c. So what do we have on the left-hand side? This is negative 10 to the negative first power equals negative 0.02 times a t value of 0 plus c. Oh, so that all just goes away. And we end up with c equals, that's a negative 1/10 there, guys. I kind of like it that way as a fraction. I suppose we could write it as a decimal too. I guess we had a decimal already on the right, so maybe I should have left that as negative 0.1. Back to where we were in blue, negative y to the negative first is equal to negative, it's a lot of negatives here, 0.02t and then minus 0.1. First thing I would do here is just divide every single term here by a negative 1, change all these negatives into a positive, all positives. Y to the negative first then is positive 0.02t and a plus 0.1. And now, everybody, remember that y to the negative first is 1 over y. All we're going to do here is flip the left side and flip, be careful now, the entire right side. So the left side just becomes y. The right side is 1 over 0.02t plus, and again, you can either have it as 1/10 as a fraction or 1/10 as a decimal. Now, perfectly fine with that answer right there. What they did, though, to make their answer look just a little bit cleaner, is they said, all right, this fraction here I believe is 1/50th, this is 1/10. They multiplied both the top and the bottom here by 50. That gave them 1 times 50 is a 50 in the numerator, and now when you distribute that 50 there, 50 times 1/50th t is just going to be t, and then plus 1/10 of 50 is going to be 5. And that's how they got their answer right here, a 50 over t plus 5. But both of those answers are equivalently correct. You get full credit for either one of them. So that was part C. And then, got to scroll up here. It's there somewhere. Here we go in part D. Determine whether the amount of substance is changing at an increasing or decreasing rate, and explain your reasoning. Okay, guys, the rate of change of the amount of substance is given by its derivative, but we want to know if that rate of change is changing at an increasing or a decreasing rate. They're asking us for the derivative of the derivative or the second derivative. So what did we know here, guys? We knew that the derivative of y with respect to t is negative 0.02, and then that was a t squared. We need the derivative of that. So d2y over dt2 would equal, okay, let's begin with the power rule. The 2 from the exponent gets multiplied out in front, negative 0.04 t, and since we're differentiating right now, we drop that exponent by 1. That's just a 1. But remember, guys, we were, nope, I wrote that backwards. That was supposed to be a y. There we go, y squared. So now that should have been a y here. But since we're differentiating again with respect to t, this is implicit differentiation, and we once again need the chain rule and a dy dt right there. And remember, guys, dy dt is known. It's this expression right here. So all of that needs to get substituted in right here for a dy dt. So this is negative 0.04y, but then multiplied by negative 0.02y squared. And all of that is going to get us a positive. Let me think here. I'm going to go back to 5th grade math. 1, 2, 3, 4 digits after the decimal point here. So my answer should have 1, 2, let me think, 3 zeros, and then an 8. So it's positive 0.0008, and then y times y squared is y cubed. Okay, guys, that is your second derivative. And with some of the same reasoning that we talked about before, let's see what we can figure out about the sign of this second derivative. Remember, everybody, that y is measuring, let me get this right here, guys, y is the amount of a substance that exists during a reaction. A physical thing like an amount of a substance can't ever be negative. So since y is always going to be positive, y cubed will always be positive, and multiplying that by a positive coefficient means that our second derivative is going to be greater than 0 for, I should say greater than or equal to 0 for all y greater than or equal to 0 as well. It's impossible in the context of this problem to have a negative value for y. And since our second derivative is always going to be positive, we know that this thing needs to be changing at an increasing rate. So let's write that out here, guys. Since d2y over dt2 is greater than or equal to 0 for all y is greater than or equal to 0, that means then the amount of substance, just trying to use their words as much as I can here, the amount of substance is changing at an increasing rate. At an increasing rate, because we found the derivative of the rate of change function had to be positive. All right, and that's part D, so that takes us through everything we needed right there for problem number 5.